Here is the final bonus multiple choice review video for Chapter 12. It says use the following information for questions 1 through 3. Recent revenue shortfalls in a Midwestern state led to a reduction in the state budget for higher education. To offset the reduction, the largest state university proposed a 25% tuition increase. It was determined that such an increase was needed simply to compensate for the lost support from the state. Separate random samples of 50 freshmen, 50 sophomores, 50 juniors, and 50 seniors from the university were asked whether they were strongly opposed to the increase, given that it was the minimum increase necessary to maintain the university's budget at current levels. Here are the results. So for question number 1, which null hypothesis would be appropriate for performing a chi-square test? Now, if you read through the options here, they're really going to go through and talk about valid null hypothesis options if it was a chi-square goodness of fit, a chi-square test of homogeneity, or a chi-square test of independence. So first we need to figure out what type of chi-square problem would this be. Now, there isn't a claimed distribution, or they're not asking if things are evenly distributed or equally distributed, so it's not a goodness of fit problem. So it's either a test of homogeneity or a test of independence, and I know it's going to be a test of homogeneity because there are separate random samples. They are wanting to test the freshman versus the sophomore versus the juniors versus the seniors and their opinion on whether they are strongly opposed to the increase or not. So I know this is a chi-square test of homogeneity, which really means I'm looking for differences between my various population groups. So the null hypothesis, the dull hypothesis, as we've been kind of stating it, would just be that all 4 populations of freshmen, sophomores, juniors, and seniors would equally oppose the increase in tuition. So I'm going to be looking for something that's talking about the populations pretty much being the same, regardless of what year in college that they're in. So for A, the closer students get to graduation, the less likely they are to be opposed to the tuition increases. Well, that's talking about differences here, that they are less likely. So it's not answer choice A. The mean number, automatically no. Chi-square problems was all about proportions, so we're not discussing mean at all, so automatically wrong. C, the distribution of student opinion about the proposed tuition increase is the same for each of the 4 years at this school. Now, this really sounds nice because they're saying that it's the same for each of those 4 years for those populations at this school. So I'm definitely liking answer choice C here, but let's take a look at the rest. Year in school and student opinion about the tuition increases are independent in the sample. This would be more of a test of independence. And then also in E, there is an association between year in school and opinion. Well, a test of association is a test of independence. So really, D and E are the null and the alternate hypothesis if this was a test of independence. So it is, in fact, answer choice C. Question 2. The conditions for carrying out the chi-square test in number 1 are independent random samples from the populations of interest. 2. All populations of interest contain at least 10 times their respective sample sizes. 3. All expected counts are at least 5. So these are legitimately the 3 conditions that we needed to check, really for all of our chi-square problems. The only little difference came in the independent condition. We need all of our populations of interest to contain at least 10 times their respective sample sizes. And in a test of homogeneity, it was the only one where we tested more than one population. So which of the conditions is/are satisfied in this case? So again, the easy one, let's check for random samples. Well, yeah, it said separate random samples. So option 1 is a go. We do have independent random samples here. Now, the independent in this scenario means that the random samples are completely disconnected from each other. That, if this freshman were selected in the first random sample, that it would in no way affect other groups of 50 sophomores, juniors, seniors from being more or less likely to be selected. Now, can we assume that there are at least 500 freshmen, 500 sophomores, 500 juniors, and 500 seniors from the university? Ooh, I don't know. What do you think? In the largest state university, I think that's going to be safely assumed to be true. Are all of the expected counts at least 5? Ooh, we don't have the expected count, so we would really need to verify if that is in fact true. But one thing I just want to point out, notice if 1 and 2 are okay, notice there is no answer choice that just says 1 and 2 only. So if 1 and 2 work and there is no 1 and 2 only option, we know the answer's got to be E in the end. But how could we verify the expected counts are all at least 5? Well, remember, we only really calculated one expected count, and that would have been the smallest expected count. Where are we going to find the smallest expected count? Well, it would be the smallest row times the smallest column divided by the grand total. Now, the grand total out of our 4 random samples of 50 people, the grand total would be 200 altogether. Now, the smallest column here is going to be 50 because there were 50 freshmen and 50 sophomores, 50 juniors, and 50 seniors. So if we have column total times something divided by 200, we need the smaller row total. So will these numbers be smaller than these numbers? And I would say no. The no's look like they're going to be the smallest grouping in here. So let's see. We got 25, there's 46, 46, and that makes 78. So 50 times 78 divided by 200 should give us the smallest expected count. And let me throw that on my calculator. And I get an answer of 19.5 would be the smallest expected count. So yes, it is true. They are all at least 5. So the correct answer would in fact be C. For number 3, the number of degrees of freedom for this chi-square test. So in a table, in a two-way table, the degrees of freedom was equal to the number of rows minus 1 times the number of columns minus 1. Well, we have 2 rows and we have 4 columns. So 1 times 3 is going to give us 3 degrees of freedom altogether. So the correct answer would be C. All right, new context. A random sample of traffic tickets given to motorists in a large city is examined. The tickets are classified according to the race or ethnicity of the driver. The results are summarized in the table. So we've got white, black, Hispanic, and other. We got the number of tickets listed out here. And then it says the proportion of this city's population in each of the racial/ethnic categories listed is as follows. So the city overall has a population that is 55% white, 30% black, 8% Hispanic, and 7% other. So which alternate hypothesis would be appropriate for performing a chi-square test? Now again, what we first need to examine is, well, which of the 3 types of chi-square problems is this? Well, we want to know if what we saw happen matches up with the claimed population proportions. So this is a chi-square goodness of fit test. We want to know, do these proportions hold true compared to our observations? So, and again, notice we are finding the alternate hypothesis. So we're going to be looking for the different thing in here, not the null or the dull hypothesis. So the racial/ethnic distribution of traffic tickets in the city is not the same as the racial/ethnic distribution of the city's population. So when they say it's not the same, that's what we're going to be looking for in here. And what they're saying in this first part is that the traffic tickets in the city, which is our first data set here, is not the same as the city's population distribution. And I think that matches up pretty good. A is looking good, but let's make sure that the others don't work out. So B, there is an association. This isn't a test of independence at all. So we're not going to be using the word association at all. And they just want to know, is there an association between race/ethnicity and the number of traffic tickets? But they're not specifying, do things match up with the population of interest here? So they're completely ignoring the fact that we have population proportions here. So it's definitely not B. C, there is a difference in the number of traffic tickets among the city's racial ethnic populations. And this sounds kind of good, but again, we're not looking for a difference in the number of traffic tickets. We can clearly see that white, black, Hispanic, and other are not equally the same as each other. And this sounds more like a test of homogeneity. We're looking for a difference among these different populations. And again, we don't have separate random samples here. D, the racial/ethnic distribution of traffic tickets in the city is the same as the racial/ethnic distribution of the city's population. Now, this sounds like the null hypothesis for a chi-square goodness of fit problem. But again, we are looking for the alternate. So it's not D. And then E, there is no difference. Well, that sounds a lot like a chi-square test of homogeneity, which again, we're not looking for a difference. So I would say it is true. The correct answer is A. Number 5, assuming the null hypothesis is true, what is the expected number of Hispanic drivers who would receive a ticket? Now, in the entire population in the city, 8% of its residents are Hispanic. And we can see that 18 Hispanics actually got a traffic ticket based on this sample, based on this random sample. But if we wanted to figure out how many would we expect to get a ticket, well, first we would need to add up how many tickets were given altogether, right? What is our total sample size here? So let me add up 69 plus 52 plus 18 plus 9. Altogether, there were 148 tickets. Now, if these tickets followed the city's population distribution for percentages here, for proportions, we would expect 8% of these 148 tickets to go to Hispanic drivers. So again, we take our sample size of 148 and we multiply it by the claimed population proportion for Hispanic drivers of 8%. And let's see, 148 times 8%, we would expect approximately 11.84 of the 148 tickets to go to Hispanic drivers. Now, can I really have 11.84 Hispanic drivers receiving a ticket? No, but it is just the expected number. So I would say the correct answer is D right here. I know some people might be very, very tempted to round this up to 12, but again, the expected number is just a theoretical value. It's not what actually truly happened. So you will not round those expected numbers to the nearest whole number. Number 6, we compute the chi-square test statistic to be 6.57. Assuming the conditions for inference are met, which of the following is correct? So now I got to figure out what is the p-value that belongs to this chi-square test statistic. So this is where you will need to be comfortable with using the chi-square CDF command. Now, realistically, if you wanted to, you could go list 1, list 2. No, I don't want to put in those percentages, but list 2, I would need to come up with all the expected counts and put those into list 2. And then I could run the chi-square GOF test and it would tell me what the p-value is. But really, we just need to take this chi-square test statistic, start with it as the lower bound, shoot off to infinity, and then we got to figure out, well, how many degrees of freedom are there? Well, in a goodness of fit problem, it's the number of categories minus 1. So there are 4 categories of racial/ethnic categories. So 4 minus 1 makes 3 degrees of freedom. So if I go find chi-square CDF, the same place I find normal CDF and TCDF, and again, start with 6.57, comma 99999 for infinity, with 3 degrees of freedom, gives me approximately 0.08694. So we are 8 to 9%. So the p-value is, where are we at? C right here. P-value is between 5 and 10%. Now again, you could do list 1, list 2, run the whole thing, but honestly, it's going to be much easier just to run the chi-square CDF command. All right, number 7, the last one with this context here. The category that contributes the largest component of the chi-square test statistic. Now, this is where when we would normally run the chi-square GOF test, we would want to see what the overall chi-square test statistic was, which was 6.57 from previously. They would tell us what the p-value was, and again, we figured out that was 0.08-ish. It would tell us degrees of freedom are 3, and then there was the CNTRB for the contributions. That's really what they're asking for in this problem. Which one contributes the most? Now, if in number 6 you did the chi-square GOF test command, well, you would have those numbers readily available to you. So you could easily look to see which one was the most off here. But otherwise, what would we do exactly? Well, we've got really just 3 answer options. We have white, we have Hispanic, and we're going to look at other. So if we were to look at white, so white and one other thing here. Remember, all of these added up to be 148. So if I wanted the expected count for, and again, let's start with whites. So 55% of 148 total tickets, the expected count, I'll put it right below here, is exactly 81.4. So I expected more tickets to be given to white drivers than what I really saw happen. So were there 12.4 fewer or 12.4 more than expected? Well, again, this is what we actually observed with 69, and we were expecting a higher number. So we actually saw 12.4 fewer. And again, if you take the difference of these two numbers, that's where the 12.4 is coming into play. So it wasn't 12 point more than expected. We saw 12.4 fewer than expected. And with Hispanic, we did that earlier, right? Yeah, we did 11.84. So let me jump back to here now. And you can see there were more than what we expected. We saw 18, but we were only expecting 11.84. So we can cross off the fewer option here. So we know it's not B, it's not C. And then other, we didn't actually calculate, but let's take a look at it. So it's 7% times 148. Its expected count is 10.36. So we saw more than what we expected, or we actually saw fewer than what we expected. So this one's still okay. This actually holds true so far. But what we're going to need to do is figure out, using that chi-square formula of observed minus expected quantity squared divided by expected, which one produces the larger value. So now just looking at these one at a time, for white, we had 69 observed. We expected 81.4. We need to square that difference and then divide it by 81.4. So let's see what that comes out to be. Square divided by 81.4, and I get that comes out to be 1.889. All right, so white is at 1.889. Now, what does Hispanic look like? So let's get rid of those numbers. So for Hispanic, we observed 18. We expected 11.84. So let's see what this comes out to be. So 18 minus 11.84 squared divided by 11.84. That comes out to be 3.205. So now we know it's not answer choice A. So it's either D or E. So now let's look at the other. We observed 9. We expected 10.36 divided by 10.36. So 9 minus 10.36 quantity squared divided by 10.36 gives me a minuscule 0.1785. So the winner is Hispanic with 6.16 more tickets than expected. All right, 8 and 9 are going to use the same context here. So it says, what is the most important reason that students buy from catalogs? The answer may differ for different groups of students. 5 different reasons are provided. Here are results for separate random samples of American and Asian students at a large Midwestern university. So you can see here are the 5 reasons. It saves time, it's easy, price is low, they live too far from the store, and there's no pressure to buy from a catalog versus in a store. You may have a pushy salesperson. And then we have our American students and our Asian students. Now, it says the top number in each cell is the observed count. So, for instance, in this first one, 29 is actually how many American students said that it saved them time. Versus, let's say, this 3 down here. It's the top number in the cell. That means there were actually 3 Asian students who gave a response of no pressure to buy as the most important reason. Then it says the middle number in each cell being the expected count. So again, going back to the American save time, we would have expected 23.60 students, American students, to say save time. And the bottom number is the individual chi-square distribution. So if I would have done the observed minus expected quantity squared divided by expected. So if I were to plug in, for instance, in that first one, 29 minus 23.6, square that difference and divide by 23.6, it's telling me I would get the bottom number. I would get a individual chi-square test statistic of 1.236. Okay, so now, question 8. Which is the correct way to calculate the missing expected count for Asian low price? So Asian low price, and there is that blank right there. So how would we come up with that specific value? And so really what they're doing here is they're doing the row total times the column total divided by the grand total. So the grand total is 157. So we know the bottom number needs to be 157. And that's not true for answer choice A. It's true for B, it's true for C, it's true for D, but it's not true for E. So we've already whittled this thing down to a 1 in 3 guess instead of a 1 in 5 guess. So now row total is 51, column total is 62. So I need 51 times 62 or 62 times 51. The order doesn't matter here. And that matches up exactly to answer choice B. Now, notice it wasn't looking for what that number specifically was because we could easily do that a different way. We know that this American low price number plus the Asian low price number needs to add up to be 51. So we could have taken 51 minus 30.86 and gotten what the Asian low price expected number would have been, which should be, 20.14? So again, if we did the math of 62 times 51 divided by 157, we should get 20.14. Now, number 9. You might go, there was another blank in there. That's number 9, which is the correct way to calculate the missing chi-square contribution for American low price. So how do we get this number? So again, they want that individual chi-square contribution. We need to do the observed minus expected, quantity squared, divided by expected. So again, remember the top number is the observed. So we really want to do 17 minus the expected was the middle number, 30.86. Square that difference, and then divide by 30.86. And again, notice they're not asking for what that number really is. They're saying which formula matches up exactly with that scenario. Well, A is doing expected minus observed squared divided by observed. So it's got everything flip-flopped around. B is looking really good up top in the numerator, but they divided by the observed instead of the expected. Then answer choice C, we finally get an exact match. For D, they're dividing by the total grand total instead of the expected count. And E was almost a good match, but notice the plus instead of the minus. So it did not work. So 9 was answer choice C. And then the last question. Which of the following statement about chi-square distributions are true? So 1, for all chi-square distributions, the probability that the chi-square test statistic is greater than or equal to 0 is equal to 1. Now, one thing we mentioned at the very beginning of the chapter in video 1 is that chi-square test statistic values are always positive. There are never negative chi-square test statistic values. So for them to say, what is the probability that we would find chi-square values that are greater than or equal to 0? Well, that would be all the time because again, there are no negative chi-square test statistics. So for that probability to equal 1, that would be absolutely true. So 1 is a good statement. Now 2, a chi-square distribution with fewer than 10 degrees of freedom is roughly symmetric. Now think of roughly symmetric kind of like approximately normal, essentially. It doesn't mean exactly approximately normal, but it means that whatever you see happening on the left side of the distribution is going to be the same on the right side of the distribution. If you were to basically cut it right down the middle, it would be roughly symmetric. Well, a chi-square distribution with fewer than 10 degrees of freedom. Well, overall, we said chi-square distributions were skewed right, but they looked less skewed right the more and more and more degrees of freedom you had. And really kind of CLT-ish idea here, I would say once we hit about 30 degrees of freedom, our chi-square distribution is going to look a lot like a normal distribution. But with fewer than 10 degrees of freedom, it is definitely not going to look roughly symmetric. It's still going to look skewed right for the most part. So I would say answer choice 2 is no good. So we can go ahead and cross off B as being an option. We know E is not going to be correct option. So now it really boils down to option 3. Either the answer is going to be A or the answer is going to be D, which again, I guess we can go ahead and cross off C. We know it's not 3 only if 1 definitely works out. So let's see, option 3, the more degrees of freedom, the larger the mean of the chi-square distribution. This again goes back to the very first video when we talked about chi-square distribution characteristics. And the mean, we said, was always going to be located at the degrees of freedom minus 2. So if you knew what the degrees of freedom were minus 2, if you found roughly where that chi-square value was at on the horizontal axis, that would tell us approximately where the mean was located. Which means if the mean is dependent on the degrees of freedom, and we say the larger, or the more the degrees of freedom, the larger the mean, that would be a true statement. The bigger the degrees of freedom, if we had 10 degrees of freedom, the mean would be at 8. If we had 18 degrees of freedom, the mean would be at 16. It would continue to get bigger and bigger and bigger. It's just going to keep shifting on further down on the right end of the horizontal axis. So answer choice 3 is a good option here. So the correct answer would be D. All right. So hopefully you got a lot out of this video. Maybe rewatch whatever questions were really tough for you. See if you can watch it again. See if it sinks in a little more the second time around. And good luck studying for your final chapter test in AP Stats.